Hello again, everybody. Today I'm going to go over the atomic force microscope called the AFM. Again, it's another scanning probe microscope. It has some similarities to this STM, the scanning tunneling microscope, but this one, the scanning tunneling microscope, requires the surfaces of the samples to be conductive, whereas the atomic force microscope, it can measure basically anything. Can't quite get down to atomic level, but it can do a good job. Here's the actual apparatus. There's the actual unit. This is just an optical microscope, so we can actually see the actual cantilever. We'll go over that here briefly. The controlling unit's right here. And this guy over here shows the actual close-up of this area right here. Now, again, here's the big picture. Literally, the setup with the laser is coming in here. It's going down to a cantilever. The cantilever is almost like the old record players from the past. It's a little needle, and this basically scans over the surface lightly. It has some force, because there are, of course, when you get on top of one another, there is a repulsive force. It's like there are attractive forces, up to a point. And then there's this like controlling box, and on here we can do all the things like adjust how magnification level, set our actual force. It tries to keep the same force as it scans over, so it's not scraping into it. And we've got the various feedback that it moves. In this case, the sample moves up or down with the piezoelectronics to keep the same force from the tip to the actual sample it's measuring. Now, here shows a little diagram. Here's the little guy right there, the cantilever. They're very thin. They're about 10 times, at least 10 times thinner than a human hair. You can barely even see them with your regular eyes. They're quite small. Here's the sample, and again, it's going to be attractive forces when you're a certain distance away. As you get closer, though, the repulsive forces will take over. And we'll show you on the other slides how this actually works. Here's the diagram showing, the forces. Again, attractive forces, the closer you get to something, it's going to go up and up and up. The repulsive forces, well, there is no repulsive force when you're a meter away, half meter, millimeter even. But once you get really, really close, then the repulsive forces, their little free space become quite large. And if you get this tip really close, close to the actual sample, you're going to get a combination of these, and at some point, this is going to be a larger value than the attractive, meaning that we have a force from the repulsion. And that's what we're doing with contact STM. It's going to be in this region here. It's also what they call tapping, where it kind of just goes up and down on the sample lightly. And that will be somewhere a little bit further distance. And that way it'll have both attractive forces pulling it towards, repulsive once it gets very close to it. All right, here's the little diagram again. We've got plenty of these. The lasers, in this case, is going through a lens on a mirror, and it's hitting against the actual tip. It's going to reflect onto a detector. As the sample goes up or down, this tip will go up or down, causing the deflection to vary where it's located on there. Okay. Here's a big blow up of the probe mount. The aluminum probe mount that we use on the AFM I have, it's about maybe 3/4 of an inch across. So it's not going to be, of course, this big. Then we have the actual probe holder, and on that, the tips are attached. So the tip, again, the cantilever is just this little guy right here. They're very small, about 10 microns or thinner. The thinner it is, the more reflexibility and accuracy you'll have from the surface. And then the actual tip itself is extremely small. It's kind of blurry, I realize, but here, one of the things we have to do is, well, before we can even run it, we've got this laser, it's fixed. We've got to move this cantilever so the laser hits at the very tip. You want to be as close to the tip because obviously as this moves up or down, this is going to have more movement than here and here. You can get the most movement at the very end. You want to put it where it's pretty much right over the actual tip to get your best realistic view of the actual thing, the sample. This shows, again, here's the AFM. There's where the laser, the tip is right there. There's my detector, this round guy. The sample would just go right in here. But again, when we're trying to align the laser onto that tip of the cantilever is so small that we need to have a nice optical microscope. This is a 60 power. We can look right through it, and I believe, yep, this is what it looks like when you're looking from the optical microscope. And you can see here, there's that big holder, which really is small. And then there's the cantilever, and there's the laser hitting the tip. So we know we have it aligned. Once we have it aligned, Well, then we need to make sure the detector is moved around to capture it as best as possible. Okay, again, there's a laser, there's the, in this case, a mirror, there's my cantilever, there's the very tip that's scanning the surface, and then there's the reflection to our detector that we then need to move around in order to get it in the middle for an average height of the sample. And then again, we have piezo electronics here. These work just like the STM one. The STM ones were actually on the tip, where the tip was. This one actually is right on part of the sample. So the sample in this case is going to move around. That way the laser and the probe can be at the exact same spot for the entire time, and no movement on those. Here shows another close-up. You can see here that that's where the laser comes from. There's the mirror. There's where it hits the tip. And then here's where we line it up to our detector. Again, the sample just slides right on in here. And then, of course, we raise it up. And so that way we're actually right underneath that, the tip of the cantilever, and it can do its scan. Here's in the other video I have, I did a little quick movie. Unfortunately, you couldn't see the laser beam very well. But this was my giant, huge model. I actually used a meter stick for my cantilever. As you can see at the very end of the meter stick, I put a teeny little tip on there. And then here's the laser. I'm not using any mirrors, I'm just going straight down. And on the video, it's hard to see the reflection, unfortunately, but you know, when I had it on a mid spot, it was right in the middle. When I had it going over a tall part, like this part right here, this raised up, of course, and the beam went up here. When I went down to the very bottom part here, well, that's when this guy went down. So we can see that from the detector, it's going to measure not only the height, but it also measures this direction as far as the angle of that particular data point. And this indicates a high surface, an average height surface, and a low surface. Over here would indicate it's bending in this direction. Over here means it's bending in this kind of direction. To get all these little multiple points, you can get yourself a nice plot of the surface that you analyze. Now, when you get to the actual module, hopefully you'll have success in using the box account I have to download the whole folder. You need to actually download the entire AFM module folder, because inside the folder there's like 482 different files mixed in there that make up this, basically a video book is what it is. Anyway, when you click on the index.html, this is what should pop up. It'll be probably, you know, like this much space with a lot of blue space. And then it's how you answer those questions. I think, you know, a list of questions that's the entire lab report. How you do it's up to you. But I would suggest probably go first to the chapters. You can click on any of these. I can go straight to just videos, straight to just theory, and ask for a couple of definitions. So you probably go to the definitions part to answer that part. But if you go right to the chapters, it'll show you here all of these. So there are quite a few chapters of this module. This was put together by one of the Purdue theory groups. Gabrielle Weaver put this one together with her group back, it's been quite a few years ago. But you can see here it's all listed very carefully about, you know, what's where. You can just click right on to whatever chapter, and then you can get all you need from that. Each chapter will have a bunch of text. It'll have images and graphs, and then there often, for a lot of them, there'll be a video on the left. If you open the video and it doesn't open up, there'll be a little thing that click here to open the program, and a separate video program will open that up for you, so you can actually listen to it. The videos, if you can't get the videos, I did put a non-video version that's much smaller on the box in case. The script should be what the text was on the videos, right? And then how you go about answering it, you can just simply watch them all and then answer them out, or you might say, oh, this one is about vacuums. You can just go, well, let's right into the vacuum. So you can do it that way as well. But as long as you get all your answers, be fairly detailed, and if it asks for any kind of like, well, draw the AFM and label all its parts, you may definitely go and do a little screen capture of one of the images that I have, even on this guy here, anywhere, and then you can just, make your arrows and text about what is what, okay? So you don't have to draw it out because you might not be very good at drawing on your computer. Just feel free to use import files of the diagram, and that'll work fine. Hope this all works well for you. I miss you guys a lot. I have a passion for teaching, and it's a lot more fun to talk in front of real people than it is in front of my camera from my phone. Anyway, hope things are good for you. We hope to have things up and running here in a month or so, but time will tell. Thank you very much. It's been a pleasure. Until next time.